Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. In the last class, we talked about the theory of plate girders. Now, in this class, we'll talk about the application of plate girders through a design example. Design of a plate girder. Design a plate girder of span 36 meters which carries service loads as shown in the figure. Use Fy equal to 250 MPa for all the steel plates. So, you can see that this span is 36 meters and it is subjected to a uniformly distributed load 18 plus 35 kilonewton per meter, and you have two concentrated loads 180 plus 400 kilonewton on the left side, which is 9 meters from the left support as well as 9 meters from the right support. The first load 180 represents the dead load and the 400 kilonewton represents the live load. Similarly, for the uniformly distributed load, the first 18 represents the dead load, uniformly distributed dead load, and the next 35 kilonewton per meter represents the uniformly distributed live load. The elements to be designed in a plate girder are: number 1, cross section, which is flange plates. As you can see at the bottom, there is a figure that shows the flanges of the plate girder. And then the next is the web plate. As you can see, again we can see at the bottom the web plate that is being highlighted. The next one is the stiffeners. Stiffeners are of two categories. The first one is called load-bearing stiffeners. The load-bearing stiffeners are stiffeners that are placed just below the concentrated load, as you can see in the picture below. This is a load-bearing stiffener, the red color stiffeners that are highlighted. Next one is the end post. The end posts are basically at the ends of the support. We are also having intermediate transverse stiffeners. Stiffeners are proposed at critical zones to resist shear buckling. So, the green color lines that are shown here are the intermediate transverse stiffeners. But as you can see that the intermediate transverse stiffeners are slightly away from the top flange as well as the bottom flange. There is a slight gap just to make sure that accidentally the load that is coming from the flange should not be transferred to the intermediate transverse stiffeners. The main purpose of intermediate transverse stiffeners is to provide resistance against shear buckling and to enhance post-critical buckling strength. This is the load diagram that shows here the concentrated load as well as the uniformly distributed load, which is step 1 for the design of plate girders. Step 2 is to calculate the factored loads on the plate girder. The factor of safety can be obtained from table 4, which is partial safety factor for loads gamma f. Here we can see that the safety factors for dead load and live load are 1.5 and 1.5. There are other loads that are taken into consideration, but for this problem, the dead loads are taken as 1.5 and the live load factor of safety is taken as 1.5. Step 3 is to calculate the shear force and the bending moment. Force demands such as shear force and bending moment are calculated for the beam with factored loads from step 2. This steps 1, 2 and 3 comes under preliminary steps or analysis, and after step 3 it is basically a design sequence for the elements of a plate girder. So, the step 4 is basically to choose the dimensions of the flange and the web plate. To ensure web depth is adequate based on L by D ratio, typically the D ranges from L by 20 to L by 12. To ensure flange dimensions are adequate to resist bending moment, B is taken as 0.3 times depth. The area of the flange is given as AF equal to M divided by D into Fy divided by gamma m naught. This is based on the understanding that the force is equal to moment divided by distance. Therefore, the force is split into area into stress equal to moment by distance D, and here A sub F is given as M divided by D into Fy divided by gamma m naught, because gamma m naught is added whenever Fy is taken into consideration. The yield stress always is accompanied by gamma m naught, which is the partial material safety factor. TW ranges from 10 to 20 mm. Step 5 is to do section classification to check if plates undergo local buckling. And the next one is to check if the web is governed by shear buckling. The corresponding provisions are given on the right hand side from IS 800 when D by TW is greater than 67 epsilon for web without stiffeners and greater than 67 epsilon into root of K sub B divided by 5.35 for web with stiffeners, where K sub B is the shear buckling coefficient and epsilon is given as root of 250 divided by Fy. Step 6 is check for serviceability to check if the web thickness is adequate for serviceability. Again, the corresponding provisions are given on the right hand side from IS 800. Step 7 is to check for moment capacity of the section. To check if the dimensions are adequate for factored moment demand, M sub D is given as Fy by gamma m naught into A sub F into D sub Cf, where Fy is the yield stress of the flange, A sub F is the area of the cross section of the flange, DCF is the center to center distance between the flanges, and gamma m naught is the partial safety factor for yielding. Step 8 is to check for the end panel ABCD to check if the shear strength of the web based on simple post-critical method is lesser than the shear force demand. So you can see that there is a plate girder that is shown here, and ABCD is the shear panel that is taken into consideration. First, we will use simple post-critical method and ensure that if the shear force demand is lesser than the resistance offered by ABCD, which is the shear buckling resistance. So the equations related to shear buckling design methods are given here based on IS 800. Step 9 is to check for intermediate panel, which is BEFC. First, let's check if the shear strength of the web based on simple post-critical method is adequate. If it is inadequate, calculate the shear strength contribution from tension field. The one that is highlighted in red color is the simple post-critical method, which is based on the elastic buckling capacity of the panel. The tension field method takes into account the additional contribution due to tension field action. Step 10 is to check for anchorage forces at the end panels ABCD. You can see that the anchorage panels ABCD at both left side as well as the right side needs to be checked for it. To check for beam action of the end panel together with the stiffener spanning vertically between the top and the bottom flanges. The vertical beam so considered should be checked to resist a bending moment M sub Tf and a longitudinal shear R sub Tf. The equations for M sub Tf and R sub Tf is given on the right hand side from IS 800. Step 11 is to design for the end post AD. To obtain dimensions B, T for end post to resist compression force due to shear force at supports and additional compression from bending moment due to anchorage of tension field M sub Tf. To check the outstand of stiffener B, buckling resistance and bearing resistance of end post. So this is also given from IS 800 page 65. It talks about the outstand of the stiffeners. It should vary between 14 TQ epsilon and 20 TQ epsilon, and it should not exceed 20 TQ epsilon, where T sub Q is the thickness of the stiffener and epsilon is equal to 250 by root of Fy. And similarly, buckling resistance of stiffeners is also given here in page 66 of IS 800, and page 67 of IS 800 gives you for the bearing stiffeners the buckling capacity. Now step 12 is to design for intermediate transfer stiffener BC. The intermediate transfer stiffener figure is given. This is a top view, as you can see from here. There is a web at the center and then there is a stiffener on either sides of the web. The thickness is T and the width of the stiffener is B. And to obtain the dimensions B, T for intermediate transfer stiffener to satisfy the minimum moment of inertia criteria for stiffness as per IS 800, the minimum moment of criteria is defined here in section 8.7.2.4. Many of these things will be much clearer when we do the design example. For the time being, please understand that there are several steps involved in the design of a plate girder. So the next one is to check the buckling resistance of intermediate transfer stiffener with the resultant force at BC. Again, IS 800 gives some certain provisions, as you can see from the right hand side. These are all screenshots from IS 800 to give a flavor of what are the provisions involved in the design of plate girders. Now let's look at step 1, which is the given service loads on the plate girder. You can see that the plate girder here is having a span of 36 meters and it is having a UDL of 18 plus 45 kilonewton per meter and two concentrated loads 180 plus 400 kilonewton acting on either sides of the span at a distance of 9 meters from the support on either sides. So the dead load calculation is UDL equal to 18 kilonewton per meter. The concentrated load W1D is equal to 180 kilonewton at 9 meters from right end, and the concentrated load W2D equal to 180 kilonewton at 9 meters from the left end. The live load is given as UDL equal to 35 kilonewton per meter. The concentrated load W1L is equal to 400 kilonewton at 9 meters from right end. Concentrated load W2L is equal to 400 kilonewton at 9 meters from left end. Step 2 is to calculate the factored load calculation, the partial safety factors for loads for limit state of strength. You can see the table 4 given below gives you the partial safety factors for loads gamma F for limit states. So the dead load factor of safety is 1.5 and the live load factor of safety is 1.5. So the factored loads for limit state of strength is given as UDL W equal to capital WD into gamma FD plus capital W sub L into gamma FL, that is equal to 18 into 1.5 plus 35 into 1.5, that is equal to 79.5 kilonewton per meter. The concentrated load W1 is equal to W1 into D into gamma FD plus W1 L into gamma FL, which is equal to 180 into 1.5 plus 400 into 1.5, that is equal to 870 kilonewton. Similarly, for concentrated load W2, we have 870 kilonewton. So we have calculated the factored loads for limit state of strength. Now the step 3 is to calculate the shear force and the bending moment diagram. The vertical reactions at supports are the summation of the vertical forces sigma Fy, which is equal to Ra plus Rb equal to 870 plus 79.5 into 36 plus 870, which is equal to 4602 kilonewton. Due to symmetry, Ra equal to Rb, therefore 2Ra equal to 4602 kilonewton and Ra equal to Rb equal to 2301 kilonewton, which is the reaction acting at either ends of the support. Now the factored maximum shear force is equal to 2301 kilonewton. Now let's find out the bending moment at the midspan. The factored bending moment at midspan is given as 2301 into 18, because 18 is the midspan length, which is 36 divided by 2, minus 79.5 into 18 into 18 by 2, which is the UDL that is acting, minus 870 into 9, which is basically the concentrated load that is acting, and the value is 20709 kilonewton meter. Now step 4 is to choose the dimensions of flange plate and web plate. The depth of the plate girder is given as L by 20 to L by 12. This is equal to 36 by 20 to 36 by 12, which ranges from 1.8 meters to 3 meters. Taking a depth of L by D equal to 13.8, we get a web depth of D equal to 2600 mm. Assume flanges resist only bending moment and web in shear. From step 3, the maximum bending moment M equal to 20709 kilonewton meter. Area of the flange plate A sub F is given as A sub F equal to M divided by D into Fy by gamma m naught. So 20709 into 10 power 6 divided by 2600 into 250 by 1.1. We get a value of 35046 millimeter square. The area of the flange is 35046 millimeter square. The width of the flange is taken as 0.3 D. So 0.3 into 2600 is 780 mm. So now let's adopt a flange plate of 780 mm into 50 mm. The area is 3900 millimeter square, which is greater than 35046 millimeter square, which is the required area of the flange plate. So it is sufficient. Let's take a web of 16 mm thickness. The web thickness should vary between 10 to 20 mm. So let us adopt web plate of 2600 millimeters into 16 mm. So we get the initial dimensions of the plate girder. The width of the flange is 780 mm, the thickness of the flange is 50 mm, the depth of the girder is 2600, basically the depth of the web, and the thickness of the web is 16 mm. Step 5 is to classify this cross section. There is section classification. For flanges, B is given as the capital B minus TW by 2. So 780 minus 16 by 2 is equal to 382 mm. So T sub F equal to 50 mm. So BF by TF equal to 382 by 50, that is equal to 7.64. So the table 2 of IS 800 gives the limiting width to thickness ratios. For welded cross section, the outstanding element of the compression flange for class 1 plastic is 8.4 epsilon. So since epsilon equal to root of 250 by Fy, which is equal to 1, so we have 7.64 less than 8.4. So it comes under class 1 plastic. So the flanges are plastic. Now for the web, D by TW equal to 2600 divided by 16, which is equal to 162.5. Now let's look at 162.5. The neutral axis at mid depth, the 162.5 is actually greater than 126 epsilon, and hence the web is slender and requires strengthening. Check if the web is governed by shear buckling. So D by TW equal to 162.5. Clause 8.4.2.1 shows the resistance to shear buckling shall be verified as specified when D by TW greater than 67 epsilon for web without stiffeners. So it is greater than 67 epsilon, which means that the web also requires check for shear buckling. Now let's look at step number 6, which is check for serviceability. Now let's look at the minimum bed thickness for serviceability. The minimum bed thickness for serviceability when transverse stiffeners are provided is a function of the stiffener spacing, which is C. So we need to assume a stiffener spacing. Here in this case, we are assuming C equal to 2500 mm, D equal to 2600 mm, which we already have calculated. So 0.74 D is equal to 0.74 into 2600, which is 1924 mm, which is less than C, which is 2500 mm, and which is also less than D, which is 2600 mm. So which ranges from 0.74 D to D. So which means that C by TW should be less than or equal to 200 epsilon sub W. So when we do so, we know that C by TW should be less than 200. So TW equal to C by 200. So 2500 divided by 200, which is 12.5. Whereas we have given a 16 mm thickness, so it is sufficient. Therefore, the web is adequate for serviceability. Now let's look at step 7, which is check for moment capacity of the section. The area of the flanges A sub F equal to T sub F into B, which is equal to 50 into 780, which is equal to 3900 millimeter square. The center to center distance between the flanges DCF equal to D plus TW, which is 50% of the flange at the top and 50% of the flange at the bottom. So we have 2650 as the center to center distance between the flanges. Now MD equal to Fy by gamma m naught into A sub F into D sub F. MD equal to 250 divided by 1.1 into 39,000 into 2650, which is equal to 23488.6 kilonewton meter, which is greater than mu, which is equal to 20709 kilonewton meter that we calculated in the step 1. Now let's look at step 8, which is the check for the end panel ABCD. Check if end panel ABCD is governed by shear buckling. Calculating shear buckling coefficient for web panel ABCD, C by D is given as 2500 divided by 2600, which is equal to 0.96. Now why do we calculate that? Because the shear buckling coefficient is a function of the ratio of C by D. So now if we have to take shear buckling coefficient Kv, we need to know whether C by D is less than 1 or greater than 1. Here in this case it is 0.96 less than 1. So we have K sub V equal to 4.0 plus 5.35 divided by C by D the whole square. So which gives rise to the value 4 plus 5.35 divided by 0.96 square, which is equal to 9.8. Now check if D by TW greater than 67 epsilon into root of Kv by 5.35 for web with stiffeners. So substituting epsilon equal to 1, Kv equal to 9.8, we have D by TW equal to 2600 divided by 16, that is equal to 162.5, and 67 epsilon into root of Kv by 5.35 is equal to 90.67. The web panel ABCD is governed by shear buckling because 162.5 is greater than 90.67. Therefore, we have to calculate the shear buckling strength of the web panel. Three components contribute to the shear strength of web V ultimate. The first one is the primary buckling strength of the plate due to elastic critical stress of the plate VCR. The second one is due to tension field action of the web. Third one is the plastic moment capacity of the flanges. The first one is basically the simple post-critical method for end panel ABCD. Capacity of ABCD using the simple post-critical method. Let's find out elastic critical shear stress of the web tau critical E, which is given as Kv into pi square E divided by 12 into 1 minus nu square into D by TW the whole square. The equation is shown on the right hand side. Substituting E equal to 2 into 10 power 5 Newton per millimeter square, nu equal to 0.3, D by TW equal to 162.5, K sub B equal to 9.8 from previous step. We have tau critical E equal to 67.08 Newton per millimeter square. Now let us find out the non-dimensional web slenderness ratio for shear buckling lambda sub W, which is equal to root of FIW divided by root 3 into tau critical E, which gives rise to the value of 1.46. Now recall, we have already understood the concept of tau B, where the tau is in the y-axis and lambda sub W is the web slenderness in the x-axis. We have a curve which is the tau critical curve, and the curve is dotted line for some portion and it is in the solid line. The solid line basically indicates the portion that is governed by Euler buckling. The dotted line basically is exceeding the capacity, and we can see that the maximum that it can reach is tau y equal to FYW by root 3, and then there is a point C which is 0.64 tau y, and the corresponding one is 1.2, and then there is a point B which basically corresponds to 0.8 in the slenderness region, and then B and C are basically connected by a straight line where linear interpolation can be carried out. So we have a curve ABCD which represents the tau B curve. So when lambda sub W is less than 0.8, it is a thick webs lambda greater than 1.2, it is thin webs, and in between the two we have intermediate webs. Here in this case, the lambda sub w is greater than 1.2. So we are using the equation tau b equal to fyw divided by root 3 into lambda w square. When we do so, we get tau sub b equal to 67.16 Newton per millimeter square. So the shear force corresponding to web buckling VCR equal to AV into tau b. This is equal to D into TW into tau b. This is 2600 into 16 into 67.16, which gives rise to the value of 2793.85 kilonewton. The nominal shear strength Vn is equal to V critical, which is equal to 2793.85 kilonewton. The design shear strength V sub D is equal to Vn divided by gamma m naught. So basically dividing by 1.1, we get 2539.8 kilonewton. And hence, we have a value of the design strength for panel ABCD is equal to 2539.8 kilonewton. And the reaction at that location is basically 2301. So the actual shear is 2301, which is less than 2539.80 kilonewton. The shear strength from primary buckling of end panel is adequate to resist the shear at end panel ABCD. Hence, the shear strength contribution from post-critical buckling is not required.